So good evening to one and all. Day 4 of our AICTE sponsored ATAL FDP program. We have started the ATAL FDP by 27/1/2025. So now it's 30. It's the fourth day. We have already completed 6 sessions from various fields. I hope the participants may know we are dealing with different kind of people, and the experts are also from different domain, and and we are fortunate to have very great experts people in all different domains. Today also we have such a great personality, and Dr. Pontikumar. He known to me for a very long time, maybe more than 12 years, from MK University School of History. So when he was at MK University as a research scholar, we have interacted and discussed many things. It was very happy time. So again, I am talking with Pontikumar with this dais. It's a really immense pleasure for me. And I am very happy to introduce the today's speaker. And he's a scientist from CSIR, Central Electrochemical Research Institute, Karaikudi, Dr. A. Pontikumar. He has many rewards and awards. He completed his PhD from Madurai Kamaraj University during the year 2014, and I got UG and PG degrees from Kandigram Rural University. And I like Pontikumar for his effortless work on e-mobility and e-vehicles. CSR has developed a lot of things, and in which he contributed very good things for that e-vehicles and e-mobility and etc. And his laboratory is also very nice. He is acting as expert and doctoral committee members etc. for many things. And he is acting as a co-editor for a journal and n number of journals. He is acting as a referee, and he completed books chapters around more than 15, and the publication is also great. Especially recently, I got the post from Dr. Pontikumar that he just crossed 9,000 citations with this age. It's a very great thing, and really appreciate Dr. Pontikumar for his enthusiastic research work. And with these words, I welcome our Pontikumar sir for this session. And audience, now it's about 1:23. I hope a few of them will join and we will start the session. Sir, for Pontikumar sir, I'm telling you, sir, nearly about 250 students have registered for this program. And regularly, there are about 200 students attending the sessions. And each sessions, we are getting the good response from the participants. And they are asking n number of questions after the sessions. Yesterday also, we have from Brooker, Ravi Kumar from Brooker, who took a session of the second one, session 2 yesterday. And after the session, the interaction was gone for about 20 minutes. So I really fortunate to have good participants and involved participants for this TEAM 2025 program. I hope the same will be there for your session also. So the session will start now, and I request you to take about 1 hour, and we can have a 10 or 15 minutes discussions followed by your session. Now it's over to you, Pontikumar sir, please.
So today I am going to talk about bismuth-based photoelectrocatalytic water splitting. So this photoelectrocatalytic water splitting is the method for green hydrogen production. So actually now the people are talking about the e-mobility. So the e-mobility is classified into 2 types. One is plug-in type, another one is the FCV. FCV is nothing but fuel cell vehicle. So for the fuel cell vehicle, the first case plug-in type electric vehicle, you have to plug in the charger and you have to charge the battery, you can drive. This fuel cell vehicle, you have to give the feedstock like hydrogen. So that hydrogen will be used to drive this vehicle. So that's why I have chosen this topic for the photoelectrochemical water splitting. Again, so now the hydrogen demand is much higher. So for that, we have to develop a technology. For that, if you are working in the lab scale, it's not sufficient to reach the commercialization. So for that, we have step forward to develop the prototype. So I will show that how we have start from the lab scale and end up with the prototype device. So before moving to my lecture, I just want to give small introduction about my institute. So I am from CSR Central Electrochemical Research Institute. So this institute is established to mark the occasion of our independence in the year 1948. So that time the Lalapa Chettiar offered 50 lakhs rupees and 300 acre lands to establish this CSAR lab in the remote place of Karakudi. So this is our 11th national laboratory. So our institute offer the final year project for a BTech student, MSc student and MPhil student. Also, we are having the sophisticated analytical instrument facility for the advanced analytical characterization. Our institute also, the academic side, beyond the research, academic side offer the PhD program under ACSER and BTech program under Anna University. So this picture is taken during that foundation day. This is the picture is taken during the inauguration of our institute. So this is our main entrance. So our core activities is related to electrochemistry. So we are our institute to provide a one-stop solution for all industrial problem with the electrochemistry. So based on that, our institute totally categorized into 6 different divisions. One is corrosion and material production, electroplating and metal finishing, electrochemical power sources, electroorganic and materials electrochemistry, electrochemical process engineering, electronics and electrocatalysis. So among these, I am belongs to that electroorganic and materials electrochemistry division. So in this division, I am leading that solar energy materials research group. So my group is mainly working on dye-sensitized solar cell, perovskite solar cell, electrolyzer and photoelectrochemical water splitting. Recently, we are working on hydrovoltaics also. So these are all the component development, materials development for the solar energy conversion applications. So this is my research group. The picture is taken during this September 2024. So we are running a lot of sponsored projects. So there are many project associate and PhD student and postdocs all are present here. So these are some of my group alumni who completed the tenure in my research group and moved to the next position. So why we have to talk about the green hydrogen production? So why? Because in the year 2016, April 2022, on World Earth Day, there is a conference is held in Paris. There, 196 country prime minister participated at the conference. Then they have discussed seriously about the big issues. So then they have concluded that the climate change is that the biggest issues we have to sort out immediately. Like that, they have make a decision. So accordingly, they have signed the agreement, and the agreement entered into the force on 4th November 2016. This agreement covers that the climate change mitigation, adaptation, and the finance. Then they have realized that why the climate change happens, because of the emission of carbon dioxide leads to greenhouse effect. So that will make that global warming. So that global warming leads to climate change. Then finally they have decided that in the year 2050 we have to completely stop that CO2 emission. So that we call it as a net zero carbon emission or carbon neutral footprint. So that's right. Then they have again they have done the discussion. So they have they have finalized that it's like the more amount of the greenhouse gas is responsible for the CO2 emission. So we have to stop this CO2 emission. So for that, after our prime minister back to our country, he announced the national e-mobility mission. So in that e-mobility mission is nothing but switching from fossil fuel based mobility to e-mobility. So that e-mobility sense, it's like this is the plug-in type electric vehicle which is available in the market. If you see in that road also, you can see this is the plug-in type electric vehicle. As like charging your mobile phone, you can charge, then you can drive. So it consists of battery pack and the battery management system and the high voltage electric cable and specially designed motor. So that you can charge and you can just drive this vehicle for your mobility. So this is one kind of e-vehicle. So you just look at this, the sales of plug-in type e-vehicle during this pandemic period, 2020 January to December. It almost 70 lakhs vehicles are sold out. So that means the people are having awareness, switching from the fossil fuel to e-mobility that will save the environment. So in that way, we can mitigate the climate change. So the middle class people also in India, you just look at this, the January to December 2021, almost 1,36,000 e-scooters are sold out. Why? Because the government is thinking that the plug-in type electric vehicle is a green vehicle. So if you use this one, it will not emit any carbon dioxide. So for that, it government announcing several attractive schemes like a tax rebate, then the cashback, then the free road tax. So likewise, they are announcing several schemes, as well as they are setting the target every year. We have to register this much number of e-vehicles. So why? Because the government is believe this, the plug-in type vehicle is a greener vehicle. But in the reality situation, this is the plug-in type electric vehicle is charging from the charging station, but the electricity is generated from the diesel generator. It seems even though it is a e-vehicle, it indirectly pollute the environment. So how we can make that the perfect e-vehicle? That is most important question. For that, I have chosen the option. So these are all the energy source. This is the non-renewable energy source. This is the renewable energy source. So this we call it as a green energy. So in this green energy, we can consider the wind or solar. But when we talk about the wind power, that will fulfill the energy demand. But the problem, it is a seasonal. You cannot get a wind throughout the year. But the solar, not like that. So India is a sunlight abundant country. It has the huge amount of energy. So we have to consider this one. Solar is the first. The second option is the hydrogen. So the hydrogen is the alternative to fossil fuel, and you can easily produce it from the water. It has high energy density also, 140 megajoules per kilogram. It has several merit over the other gases. It has that high energy conversion efficiency. You can easily produce it from the water without emission. It is a earth abundant. You can easily store it in different form like a gaseous, liquid, or a solid form. Also, you can use for long-term transportation purpose. Also, you can use it. So the hydrogen can be classified into different type based on the color code, based on the production method. So now normally the hydrogen can be produced by three different methods. The first method is a coal gasification. The another one is steam methane reforming. What are the hydrogen is available in the market that is produced through these two methods. And recently now the people are producing hydrogen by using the electrolysis process. Okay, so how we can give a color code for this hydrogen? So suppose you are taking a starting material as a coal, you are doing coal gasification, you are producing the hydrogen. Then during the production, CO2 is emitted to the environment. So in this case, this hydrogen is called as a black or brown hydrogen. Suppose the emitted carbon dioxide that can be captured and stored, that will be called as a blue hydrogen. Again, when we talk about the natural gas, like a hydrocarbon, methane, so you can take that will be you can do it by steam methane reforming method. You can produce hydrogen and it release the carbon dioxide. It is called the gray hydrogen, or it is captured. It is the blue hydrogen. When we talk about the electrolysis process, if you are using the electricity which is produced through the nuclear power, then it will create a nuclear waste. Then this kind of hydrogen production is called the pink hydrogen. Suppose if you are using the renewable energy like a solar or a wind power, then if you are doing the electrolysis process to produce hydrogen, the byproduct is oxygen. Then finally it is called as a green hydrogen. Now you just look at this. This is also e-vehicle. It is called as a fuel cell vehicle. So it is a fuel cell train running in Germany. This is Toyota Mirai car is running in Japan. So it is a zero emission bus running in the United States of America. This fuel cell is not only for the public transport. You can use for the logistic purpose. So it is a Hyundai truck. So just to look at this, how this vehicle is working, let me see the working principle. So It is a cross-sectional image of this is the cross-sectional image of this fuel cell vehicle. So it has that the battery and the hydrogen storage tank and the fuel cell stack, boost converter, power control unit, specially designed motor, and a specific membrane that will allow only oxygen from the environment. As soon as you ignite the vehicle, what happened? The hydrogen from the hydrogen storage reach the fuel cell stack and oxygen enter into the other side of the fuel cell. So both the hydrogen and oxygen will combine together. It will produce the electricity. That electricity is used to drive this vehicle, and the byproduct will be the water. Okay, so how this electricity is produced? We just look at this. This is the fuel cell single unit. So it has that anode and the cathode, as well as there is a membrane. Okay, once the hydrogen is passed through this fuel cell, it reaches the electrode. This the hydrogen is converted into proton and it emits the electron. These electrons are collected as a electricity. So this electricity is used to drive this vehicle. Then this proton will attract this oxygen and it releases as a water. So the water is a greener product. When we talk about the mileage, if you use 1 kilogram of hydrogen, then you can drive up to 100 kilometers. So this is the mileage of this fuel cell based vehicle. I will show a small video for your better understanding how this fuel cell vehicle works. Again, when we talk about the merit of this fuel cell vehicle over the plug-in type electric vehicle, you want to charge the battery in the plug-in type vehicle, you have to wait at least 3 hours so that you can drive 400 kilometers. But when we talk about this fuel cell vehicle, just like filling a petrol, it will take just 3 to 5 minutes. So likewise, you can fill 4 or 5 kg hydrogen within 3 minutes. Then you can drive up to 500 kilometers. So the waiting period is not required for in this case of hydrogen. Hydrogen-based fuel cell vehicle. Is the video visible?
Yes, yes.
Okay.
Yes, Dr. Bhan, it's visible.
So this vehicle is working based on the simple chemical equation. So you just take a hydrogen and it mix with the oxygen. Finally, it produces water, and meanwhile, it is electricity. For producing this electricity with this two, you need a device. That device is called the fuel cell device.
இந்த கூத் பண்றத ஜாயின் பண்ண முடியலன்னு போட்டிருக்காப்ல. So here you can visualize how that hydrogen and oxygen combine together, it produces electricity.
Now you may get some idea about the working principle of this fuel cell vehicle based on that video. So if you are having the hydrogen, then you can use it as a feedstock. Then you can drive this vehicle. So that is the merit. So again, if you look at this, the byproduct will be the water. So it will not pollute the environment. So these are the advantage of this one. But whenever talking the positive point of the certain things, we have to see the other side. So when we talk about the dark side of this fuel cell vehicle, so you just look at this. This is the Toyota Miracar, what you have seen in that video, that had an accident. Then immediately the hydrogen storage tank got exploded. Then immediately it catches fire. Again, there is another incident in Norway, improper handling and storage of this hydrogen. The hydrogen fueling station got exploded. This is the another incident. Then later, the people are thinking about the hydrogen storage aspect. Then they have come out with that the excellent hydrogen storage tank that contain high density plastic, carbon fiber, glass fiber, polymer foam, and flame resistant composite material. Finally, they have end up with the very good excellent material for storing the hydrogen. So then after installing this hydrogen storage tank into the car, then the Hyundai company, they have done the crash test. Then the crash test, the hydrogen storage tank doesn't get exploded. The car got only physical damage on the plastics only. Okay, so now we never bother about this hydrogen storage and this kind of accident and other things. So it is now it is a safer side, but still I just want to give a warning, so that I just want to put these two pictures. If they see these two pictures before purchasing, then they would don't go for buying this fuel cell vehicle. So you never bother, but there is a possibilities is there. Then you may ask that, sir, what are the things, the vehicles you are showing that is running in abroad only? So any technology in abroad, it will take at least 1 decade to reach the India. When we will get this kind of technology? Then actually in the year 2022, our CSAR SICRI scientists, in collaboration with our sister concern laboratory NCL Pune, together we have developed this fuel cell stack, which is the materials and resources available within India. Nothing will be imported. So all will be, we have collected within the India, we have assembled and tested, validated, and we transfer this technology to KPIT, that is the Sentinel Lab. So this is the zero emission fuel cell bus. So this is the technology. Again, the another story, you just look at this. This technology further is transferred to the Tata Motors. The previously in the year 2018, the Tata Motors developed 5 fuel cell based bus. So that will be dedicated to Indian Oil Corporation employees. This is the picture, plug up picture. Then this is the another picture. It's taken during the last year. It is a flag off ceremony of India's first hydrogen fuel cell bus. So that is dedicated for the IOCL employees. It will be used as a shuttle bus. So here the Ministry of Petroleum and Natural Gas, that will be sponsor for this. The Tata Motor take the lead to developing this bus. But when we talk about these two bus, there is a difference. So this bus is a hydrogen fuel cell bus, but they have utilized gray hydrogen and blue hydrogen. That means while producing the hydrogen, this will emit that carbon dioxide. So that hydrogen only they are using here. So if you are using this one, what you have seen in that the plug-in type electric vehicle that is charging from the charging station, that is powered by diesel generator. The same story, you are somewhere you are releasing the carbon dioxide, but you are saying that it is a green vehicle. But when we talk about this particular vehicle, this vehicle is launched in the last year. So you just look at this, India's first green hydrogen fuel cell bus. So it seems like this bus is completely run by the green hydrogen. Okay, so they are utilizing the green hydrogen, which is produced by electrolysis method. That power is generated from the solar cell or wind power. Okay, so that is the difference between. So now in the road we can made it. So now the technology to the road. So we never bother. So the main idea, if you use this rather than using so many vehicles, you can accommodate all the people. So they made it the free shuttle bus. So this is the prime idea. Okay, so this story is not only stopped in road. So we have just to move our scientists just to move to the next level. It's like if you visit Cochin, there you can see that the marine metro. You can see that the Asia's first marine metro in Cochin only. So there the marine metro is normally run by the plug-in type e-vehicle. So that is battery operated. The catamarans they are using for the marine metro. But the first time in the last year, February 28, our Prime Minister he flagged off this hydrogen fuel cell powered passengers catamaran. This is also completely run by the green hydrogen. So this technology also developed by our CACR Sikri and our NCL Pune together. So we have developed this one. So this is another success story. So we have completed from the road as well as water. Now we are trying to move to the track. So you just to look at this, we are expecting in 2027, 2027, we are expected to launch this the hydrogen powered fuel cell train in the railway track. So this is the another story. Okay, so now you know that we are having the technology, everything. So in this case, if we are completely moving to fuel cell based mobility, what is the hydrogen demand? That is the important question. So we are now in the middle of this 2020 and 2030. So now the hydrogen demand is 70 million metric ton and maybe nearly 100 million metric ton by 2030. But as per the Paris Agreement, which I shown in the first slide, we are going to achieve net zero carbon footprint by 2050. That time the hydrogen will open the several avenues in the power generation, especially the transportation sector. What we are consuming the hydrogen at the moment almost double. So overall, if you look at the hydrogen demand, it's almost tenfold, nearly ninefold is higher what we are consuming this one. So now itself we have to get ready for the hydrogen production technology. Then let me see this what is the technology available for the hydrogen production. So when we talk about the scientists from DST or DRDO or CSIR or ISRO, so we talk about the technology. We will not disclose I have this much hydrogen production rate, I have this much power efficiency, I have this much storage capacity. Likewise, we never talk about the device. So if we meet together, we will ask, wow, which field you are working? I am working in solar cells. What is your TRL level? So the fellow may say that my TRL level 5, then he might be in the transition between the demonstration of technology or something. So we can assume that. So in that way, in order to validate the technology, you have to use this TRL scale. So what are the hydrogen is available in the market? That is the TRL level 7 to 9. So it is like a steam methane reforming, autothermal reforming, coal gas. So these are all blue hydrogen and gray hydrogen. So the alkaline electrolysis and the PEM electrolysis just reached the mature state. So that is the technology transformation development stage. So that only. When we talk about the solar to hydrogen production, it is still in the lab scale. Lab scale is nothing but a person doing some experiment and writing a paper, publishing a paper in some good journal. That is maximum TRL level 3. So suppose the MSc student doing project, submitting thesis, so that is the TRL 2. So this is what the different TRL level. So now the TRL level for the green hydrogen production is very, very low. It is in the stage. So for that, our Honorable Prime Minister, he announced the National Green Hydrogen Mission. So this green hydrogen mission to make India a global hub for the production and export of green hydrogen. For that, he announced 800 crore budget for this activity. But in the year 2023, our Union Cabinet approves this National Green Hydrogen Mission with the total outlay of nearly 20,000 crores. So these are the expected deliverables by 2030. So India can produce the green hydrogen 5 million metric ton per annum. So we have to increase the capacity up to this. Then we can increase the electrolyzer capacity up to 100 gigawatt. then you can increase that the renewable energy. Why? Because the electrolyzer use that the renewable energy. So for that they are making the renewable energy sources. So but it requires very little amount of the energy for this producing this hydrogen. The rest of the energy will connect to the grid. In this way 125 gigawatt of energy we can increase. Now these are the direct benefit. So indirect benefit, we are moving to the fuel cell based mobility. So in that respect, we are using hydrogen as feedstock. So we don't want to go for the this one. Other activity. We can stop the import of crude oil worth of 1 lakh crores. We can save, right? Then 50 million metric ton of hydrogen also per annum we can minimize. And also you can increase the job opportunity, almost 6 lakhs job per annum you can create. Then we can get a corporate investment 8 crores per annum. Over the period we can get a corporate investment for the 8 lakhs crores. So I will give one small example that happened in the recently, so that I will show you for the last 2 cases. So last year our Chief Minister of Tamil Nadu, he visited the United States of America. Then he signed the MOU with that Omium company. So the Omium company already having the factory in the Sengalpattu as well as Bangalore. So this Omium company is a typical company for the production of green hydrogen. So they have signed the agreement. Then they want to set another new factory in the Sengalpattu. So already they have one factory in the Sengalpattu. So now they want to invest 400 crores on that. This can offer the employment for the 500 individuals. So this is the typical example for the last 2 cases. Likewise, many cases already happen in the North India itself. Again, you just look at this picture. This fellow is a Chokalingam. He is an alumni of our BTech. He is a Sikri alumni. He is the executive director of this Omium company. So he also involved in this one. So this is one typical example. So you don't restrict this green hydrogen only for e-mobility. So I will show one example. Recently, my student, one of my students went to represent this green hydrogen production related activity in that conference organized by 5 different ministries at the Bharat Mandapam, New Delhi. So she may see that they have showcased one hydrogen powered truck. So that is developed by our Ashok Leyland from India itself. So that truck is not a e-vehicle, that is not a fuel cell vehicle. So they have modified the existing truck by like IC engine, so internal combustion engine. They have modified that one. Then they have used the hydrogen. So they can run the truck for the logistic purpose. They have showcased and demonstrated in that so my student take some picture or something. After sometimes he came and told me, sir, now the people are doing without e-vehicle, this hydrogen can be used. So that's why our government want to invest that much 20,000 crores money on this particular activity, like a green hydrogen production activity. So I will show another video how the truck that is a non-e-vehicle, how they can utilize this hydrogen for the transportation purpose. I will show another one video.
On the road that leads to the dream of greener mobility, the world now gets a new set of wheels to steer that journey towards reality. Presenting Ashok Leyland's pioneering technology, the hydrogen internal combustion engine vehicle that's built on the ATAL modular platform. The fuel delivery system on this vehicle is modified to use green hydrogen instead of diesel. A strong carbon fiber composite cylinder ensures safe storage and high pressure endurance of up to 350 bar. That's extremely easy to install, lightweight, and maintenance-free. With minor changes to our H-series 6-cylinder internal combustion engine, we are able to deliver power and torque equivalent to a conventional engine. With a lean combustion strategy, It ensures minimal emissions and less noise, resulting in an efficient, cleaner, and a quiet drive. The hydrogen internal combustion engine vehicle delivers the highest payload and long range. Its aggregates are similar to a diesel vehicle, aiding easier maintenance, complementing the hydrogen mission that supports the Atmanirbhar Bharat initiative. These benefits make hydrogen internal combustion engine vehicles a perfect vehicle to drive us towards the future. अशोक लेलैंड, कोई मंजिल दूर नहीं.
So now you may know that the hydrogen is how much important, especially in the transportation sector. So that's why we have to develop the technology for the green hydrogen production. That is most urgent to fulfill that the future hydrogen energy demand. Okay. So how we can produce the hydrogen by using the sunlight? It is very simple. You just take a semiconductor, put it into the water, expose to the sunlight. Then this will produce hydrogen and oxygen. But when you look at this equation, it is very simple, but it involves two complex reactions. One is a hydrogen evolution reaction that involves 2 proton and 2 electron. Another one is oxygen evolution reaction. It involves 4 electron and 4 proton. So involvement of this 4 proton and 4 electron, it is called as a rate determining step. So overall, you want to split the water, you need 1.23 volt. Okay. Then how this semiconductor can split the water? You just to look at this, the semiconductor have the conduction band and the valence band, right? So when we talk about the energy level, the conduction band should be above that the hydrogen evolution potential, and the valence band should be more positive than the oxygen evolution potential. Upon illumination with the sunlight, it will undergo charge separation, and holes produced here, this holes oxidize the water and produce oxygen and proton. Then the proton is moving here, the electron is here, this electron will reduce the proton into hydrogen. So this is what we can produce the hydrogen. So here this semiconductor simultaneously produce hydrogen and oxygen. So we call it as a bifunctional catalyst. So this terminology is the bifunctional catalyst. Then again, when we talk about this, you may ask that, sir, you are saying that both should be above and below. What happened? This conduction band is below, or what happened? This valence band is above this potential. So you just look at these two examples. So if it is a conduction band below, it cannot produce hydrogen. Then we call it as a oxygen evolution catalyst, OER catalyst. When we talk about this case, it cannot be able to produce oxygen, but we call it as a hydrogen evolution catalyst. Normally, the semiconductors are two type, P type and N type. So when we use that N type semiconductor, we can use it as a photoanode in the photoelectrochemical cell. When we use that P type semiconductor, you can use it as a photocathode. When we are having both electrode, you can use it in a tandem cell. So usually, for the first time, the Honda and the Fujishima, they have together, they have developed this photoelectrochemical cell for water splitting for the green hydrogen production. So this cell contains two compartments, one compartment anode, another compartment cathode. Both compartments will be separated by proton exchange membrane. This anode and cathodes are connected through the circuit. Upon illumination, the semiconductor oxidizes the water and produces oxygen here. Then the proton moves towards the proton exchange membrane. It accepts the electron and produces the hydrogen. So suppose you want to start your career in this particular area, especially the hydrogen production by sunlight, then you have to consider these 4 criteria. First one is suitable optical property. What is that? Actually, the solar spectrum having the IR radiation, UV radiation, and visible. So IR radiation produces heat, so we don't want to use it. Then if you use that UV, it is only 6% or less than that. So we have to design the catalyst which can absorb in the visible region. This is the first criteria. Then suitable bandage alignment. The suitable bandage alignment is nothing but it's like you have seen that the HER catalyst, OER catalyst based on this band position. So likewise, you have to choose the catalyst band position like this accordingly. Then the charge separation migration. Once you illuminate the sunlight, immediately semiconductor undergo charge separation. Then the electrons should be migrated to the current collector. That is the another criteria. You have to check the literature accordingly. Then the final one, your material should be stable against the photocorrection. Okay, so these 4 criteria is most important thing. So I just skip this slide due to the time limitation. So our interest is the bismuth based material. So the bismuth based material can be classified into various types. Why? Because our interest on this, if you look at this, the valence band are more positive than the oxidation evolution potential, that is favorable for water oxidation. If you make this water oxidation is more facile, then you can increase the hydrogen production rate. So this is what our interest. But when we use this single semiconductor, the problem, it will suffers from the charge recombination process. In order to avoid this, so as a result, the efficiencies get decreased. To avoid this, we can do this kind of modification, like you can do doping or you can alter the stoichiometry, that is component adjustment. Then other strategies is surface modification. You can modify the surface with some conducting material, or you can tune the morphology accordingly. You can tune the surface area, you can increase the activity, or else another activity is that forming the heterojunction. So our interest is forming the heterojunction is our approach. So like you just look at this is the simple photocatalyst. Here one person is standing and jumping and again reaching the ground due to this the gravitational force. Likewise, if you take single semiconductor, due to this Coulombic force, this electron and holes will be recombined together. Finally, the net result will be 0. Suppose you just look at this, here you are adding a table, you are jumping and standing on the table, then it called as a he is spatially separated from the gravity. So likewise, you can add the semiconductor, accordingly the electrons and holes will be separated spatially. Okay, then you just look at this, what are the types of heterojunction. So the heterojunction classified into 3 types, type 1, type 2, type 3. So based on this band position, accordingly you can classify this. Other than that, you may know that the semiconductors having p-type and n-type, then p-n heterojunction. But this system is more effective. So why? Because when we come to the contact together, so it create an internal electric field at this space charge region, that is the interface. So as a result, the electrons are moving towards here n-type, and these holes will be moved towards the p-type semiconductor. Then the last one is just heterojunction. Actually, the previous case type 1, type 2, type 3 and the PN heterojunction, that will be used for stepping down the electron and stepping up the holes. But some reaction is thermodynamically is not favorable. You have to step up the electron and step down the holes. So that is the most important thing. So for that, accordingly, the band position you have to design. You can add a mediator accordingly. Here you are stepping down the electron, again you are stepping up. So likewise, here also you can see. So this is what, suppose you are adding the mediator, so it is the mediator based jet scheme. If there is no mediator, it is a direct jet scheme mechanism. So these are the heterojunction. So what kind of material I can use for the heterojunction, forming a heterojunction? You can see plenty of catalysts, but my interest the graphitic carbonator, since it is a metal-free photocatalyst which will absorb in the visible region, the band gap lies 2.7 to 2.8 electron volt. So it is a metal-free, non-toxic, low cost. You can easily tune the band gap. Again, this it can be classified into 2 different structures. These structures are proposed by Bergelius and Liebig. So the first structure is a triazine-based graphitic carbonator. The second one is heptazine-based graphitic carbonator. This can be easily prepared by 2 different methods, the top-down approach and the bottom-up approach. Okay, so the top-down approach is nothing but you take a bulk material, you can do exfoliation, finally you will get a nanoseed. Suppose you take molecular precursor method containing the carbon and nitrogen. So melamine, cyanamide, dicylamide, urea, thiourea, whatever the precursor you can take. Directly you can calcinated at 550 degrees Celsius, then you will get a yellowish color heptazine-based graphitic carbonator. I'm not going to detail about this mechanism, degradation mechanism. So you can easily control the morphology by adopting the different methods, choosing the appropriate precursor. Accordingly, you can tune the morphology and the surface area. Okay, so I will give some of the example what we have done in our lab for this heterojunction for the production of green hydrogen through the photoelectrocatalytic water splitting. So I have taken the melamine mixed with the ammonium sulfate, and then finally subject to the calcination to degree, I got a graphitic carbon nitrate nanostructure. Then this will be mixed with the bismuth nitrate and ammonium molybdate subject to the solvothermal treatment. We are able to get the heterojunction of these two. So this is the pristine bismuth molybdate. This is after modifying, forming a heterojunction with the graphitic carbonate. Here you can see that the graphitic carbonated formed over the surface of this bismuth molybdate. Then the elemental mapping clearly confirmed that the different elements present in the heterojunction material. This XPS analysis shifting in the binding energy for as compared with the pristine material and the heterojunction composite material that reveals that the formation of heterojunction and the strong interaction between these two materials. When we talk about the crystal property of this material, after adding this graphitic carbon nitrate, it will not alter the crystalline property. That is the orthorhombic structure of bismuth molybdate. This one that is still persists, so it doesn't alter the crystalline property. Then the carbon nitrogen functionality that we have confirmed through the FDR studies. So the systematic changes in this one, the functionalities exist. Then we have done that the wettability analysis to check that the interaction between the water and this prepared material. So it seems the pristine material shows that the high contact angle bismuth molybdate after making this composite with this the contact angle is get reduced. This is due to that the carbon nitrogen functionality that will make the carbon hydrogen bonding with the water, so that will make it more wettable. Likewise, after forming the heterojunction, here the surface area is increased as compared with these two materials. So then we have done optical studies. So in the optical studies, it seems that it shows that the visible light absorption property, as well as by changing this graphitic carbon nitrate, that will influence the band gap values with respect to different to this one. Then we have done that photoelectrochemical water splitting. So we have done that the characterization, the absence of light. So it's just look at this. This is the controlled samples. This is the variation in the samples. So there is a poor response in the photocurrent, but after illuminated with the light, the photocurrent goes up, it increases significantly. So we have optimized 10% for higher activity over this surface. So the charge separation and the migration aspect we have done by choped illumination through the linear soap voltammogram. So here rise and fall in the photocurrent with respect to this one increase. Also we have checked the durability. It shows that after several cycles, it shows that the best reproducibility with respect to the time. Then the impedance analysis shows that the smaller semicircle, it shows that the high interfacial charge transfer rate and minimum charge transfer resistance occurs in the fabricated electrode. Then the efficiency we have calculated for the different system. Then it seems 10% shows 7-fold and 20-fold higher efficiency than the pristine material. Then we have arrived at the type 2 mechanism based on the calculation and the values which is derived from the literature. So the psi value we have taken from the literature for material. Then we already calculated the band gap through the tax plot method. So we have substituted these values in the particular equation. Accordingly, we have derived this band position of both the material. So finally, this position shows that the type 2 mechanism for this one. So this particular work we have done, the materials we have prepared as a powder, then we have used the fabricated the electrode. Finally, we have carried out all the experiments. So that's why we got the poor response of this, poor performance of this material. Then we have shifted to the thin film based method. So in this case, we form the heterojunction between the bismuth vanadate and the copper oxide. So here the bismuth vanadate electrode is fabricated by electrode deposition method, and again forming the heterojunction also carried out by electrode deposition with the copper acetate and acetic acid. So the XRD peak, the signature peak, it reveals that the clear formation of copper oxide over the bismuth vanadate surface. So this is the pristine one. This is that after forming the heterojunction. Then the FECM analysis shows that the excellent morphology for the before and after deposition of copper oxide. The elemental mapping also conclude that the existence of only 4 elements in the thin film. Then the XPS analysis, especially we want to prove the formation of heterojunction. So after forming the heterojunction, the shifting in the binding energy, it leads that surface charge transfer between these two leads to the formation of heterojunction. Then the band gap value and optical studies also we have carried out by adopting Max plot method. So here after forming the heterojunction, visible light absorption enhanced for this bismuth vanadate. Then we have carried out this photoelectrochemical water splitting experiment. So in the dark condition, it shows that the poor response, but upon illumination, it shows that the higher photocurrent response. So previous case, we have used powder samples so that we got the current response in the 25 microampere, but we are able to get here like 2.5 milliampere. It's almost like 100 times higher than the previous one. So after making this one, so the charge transfer separation property also we checked by chopping the illumination through the linear sweep voltammogram. Then we want to see this the charge surface transfer efficiency by adding the sacrificial agent into the supporting electrolyte. Then we have performed this photoelectrochemical water splitting. So here we are able to see this after forming the heterojunction, almost to double the increment in the surface charge transfer process. Then we want to derive the mechanism. For that, to know the band position of this valence band maximum, we have done the XPS UPS analysis through the valence band spectra through the UPS mode. So for the both the semiconductor, then we have done Morse-Schottky analysis for the measuring the Fermi level of the both the semiconductor. Then we have substitute all the calculated values in this particular formula. Accordingly, we have arrived the valence band maximum and the conduction band minimum for both the semiconductor. Then we have come out with this band position for the both semiconductor. So this is before contact. After forming a contact, so the Fermi levels are undergo equilibration and the internal electric field generated at the space charge region. Then finally we have arrived at PN heterojunction mechanism. Excuse me. So the stability also, it shows that the excellent stability, durability, you can see that the hydrogen production rate is good, as well as the efficiency, we also got nearly 1% efficiency. It is closer to the benchmark value in this case. So we have developed several systems for this photoelectrochemical water splitting. So we adopted both two strategies, like we synthesize the material through the powder form, it is coated over the electrode, then we explore this this photoelectrochemical performance. You just look at this, the values are very less hydrogen production rate. Likewise, the efficiency also, you just look at this, it is very poor. So upon introducing the thin film fabrication strategies, you can see this, the values are very closer to 1, as well as you can see it is almost 40-fold higher than this thin film shows that the 40-fold higher. So then we conclude that the fabrication of this thin film based technologies are promising for green hydrogen production. Then so what are the results we have done? I have discussed so far. So that is comes under TRL123. So I have carried out all the experiment, then concluded the measured the hydrogen production rate, then published as a paper. So I am still standing here only. Then how I can move here to here? That is the question, the higher TRL level. So for that, we know that the bismuth vanadate shows that the higher photocurrent, normally 1 centimeter square deliver the efficiency also nearly 0.1% and 1 milliampere current density it shows. So that's why we have chosen. Then we have fabricated an electrode from 1 centimeter square to 25 centimeter square. Then we have developed this prototype device by using the acrylic sheet as well as the quartz window. Then we use this Nafion N117 membrane. Then we have constructed this photoelectrochemical prototype. Then we examine the performance. When we increase the area, it seems the current density is increased. That means the hydrogen production rates obviously higher than this one among these. So likewise, when we increase the area, obviously the hydrogen production rate will be increased. But I just want to see, suppose this 1 centimeter square can produce 100 hydrogen, whether this 4 centimeter square can produce 400 hydrogen. I just want to confirm. Then what I did, I convert all the current into current density. Then when we see this, the pattern will be totally reversed. Why? Because if you look at this, obviously this 4 centimeter square produce higher hydrogen than the 1 centimeter square hydrogen, because 1 centimeter square can produce 100, but this 4 has to produce 400, but it produces 150 or something, then it shows higher value. But when we converted it to the current density, it totally the trend will be reversed. So that means some losses are there. So that means if it is able to produce 150 hydrogen, then 250 hydrogen losses is there. So that we have to fix it. Then we want to see this, how we can fix it. Then somewhere I have gone through the Facebook. Then while scrolling the Facebook, I have seen this picture. Then I got the idea. Then accordingly, I have modified my electrode. Rather than the plain electrode, we have made the grid pattern. Accordingly, we have come out with this kind of electrode. Then when I use the plain electrode, when we go with the 4 centimeter square, 20% loss. When I reach 25 centimeter square, almost 50% loss in the efficiency as well as the hydrogen production rate. So after we modified the pattern, so this is the 25 centimeter square. So but 1 centimeter square shows that the higher activity. So if we use the plain one, the charge transfer resistance high, charge recombination, those factor will bring down the efficiency below 50%. So we have modified the electrode fabrication, making line pattern and grid pattern. So this will be act as a 5 electrode. This will act as a 25 electrode, or 25 1 centimeter square integrated like that. So accordingly, we have performed the experiment. So now you can see that when we use the plain electrode, 51% loss. When we move to the line pattern, again 10% we are able to save. Then we move to the grid pattern, it will be 27. Then after that, we are adding the sacrificial agent, the sodium sulfate into the electrolyte. We are able to reduce the efficiency loss less than the 20%. So when we are moving to the prototype device, rather than the one lab scale device, if you are having the efficiency loss less than 20%, it is a promising one. We can go for the scaling up process of the hydrogen production. So that we went for the pattern. So we have submitted a pattern for this particular work. So this prototype development, it shows that it is a TRL level 4. So further, if you are integrating more amount of, if you are stacking more number of electrodes, then we are making the stack. Then it will be TRL 5. So likewise, the TRL levels will be moved. So this is what this one. So then when we go for the full cell analysis, it shows that when we increase the voltage, applied voltage, so the hydrogen production rate is increased as compared with that previous case. It is in the full cell. So this is the overall summary of my presentation. So it's like initially we have talked about the importance of hydrogen and why the hydrogen mission is needed, and how this photoelectrochemical cell works and how it will help to produce green hydrogen. Then we have discussed about the material screening for the photoelectrochemical water splitting, and I have shown some of the result in the lab scale level, the materials which we have developed in both the powder form as well as thin film form and its performance. Finally, I have shown that how we have achieved the prototype device for the photoelectrochemical water splitting. So this is the end of my presentation. So this is suppose if you are really interested to work on this heterojunction material, you can refer this book. Is edited by me, or if you need, you can send the request. I will share the soft copy with you. Then this is the publication tracks we have come out from the lab scale from the prototype. So we have come across all the publication. Accordingly, we have judged this thin film fabrication is the promising for developing the prototype. So finally, we have ended up the prototype with the pattern. So for this investigation, my PhD student is awarded for the best PhD thesis award, especially this particular case, rational design and fabrication of bismuth-based photon for photoelectrochemical water splitting. So the another recognition for my contribution in this photoelectrochemical water splitting, it is recognized by the Academy of Science Chennai, offered the Young Scientist Award 2023 last year. Then another recognition, as already mentioned, that my student went at the conference organized by different ministries at Bharat Mandapam. She represented by the green hydrogen production. Then she got a third prize with the cash price of 20,000. There only she have noticed that the hydrogen powered IC engine based the Ashok Land and the truck, hydrogen powered truck. Then the another recognition for this green hydrogen activity, the one of my student has been nominated by the DST to attend the meeting at the German to participate with the Linde Nobel Laureate meeting. So in the upcoming month. Okay, so finally, I would like to thank my institute director for his appreciation and support on this green hydrogen related activity, and I would like to thank my head of the department for his endless support in the particular aspect. Then the staffs from the central instrumentation facility for the advanced characterization facilities. Then finally, I would like to thank all the funding agencies for getting a different project through different equipment for integrating this particular area, especially what are the results I have discussed here. This is the output from the DST hydrogen and fuel cell and the CSER first project. Then I would like to thank all my students for their endless effort and hard work for reaching our research group in India at the TRL level in the green hydrogen production with the photoelectrochemical water splitting. So before closing my talk, this is the take-home message. You have to move to the e-mobility that will be powered by the fuel cell. So the fuel cell feedstock will be the green hydrogen that is produced by electrolysis of water with the aid of say either sunlight or by wind energy. Thank you for your kind attention.
Thank you, Dr. Pandikumar, sir. It was power-packed presentation, and you given a lot of data. It was very interesting to know about that renewable energy sources and how to use it, and especially the videos that you have shown. I hope the participants have enjoyed.